So just as a brief summary, again, we're making these non-ohmic devices ohmic, right? How do we define Ohm's law in exactly the same way? Voltage is equal to the impedance now times the current. But the impedance is just the voltage over the current. For the capacitor is just 1 over j omega c. For the inductor is j omega L. And then if we have capacitors, inductors, resistors in series or parallel, we can figure out what the equivalent impedance is. So now let's look at the voltage divider. Right, this is something that we've seen before. We have the voltage divider. We'll imagine there's some current, and we'll imagine for the instant of time we're thinking about it, current goes clockwise. We can write down Kirchhoff's loop rule. There's the potential signal generator plus the potential across impedance 1 and impedance 2. We can apply our Ohm's law. We can find the current. Once we know the current, we can find the potential across each of the elements. And the upshot is it looks exactly the same as the voltage divider before, only the impedance, instead of resistances, we have the impedance of the elements. And so it doesn't matter if they're inductor or capacitors or resistors, we can treat them the same way. Now these are a little more complicated, right? The impedances are imaginary and they vary with frequency, but the idea is exactly the same. So let's look at a specific example. Let's take a 10-volt signal generator, 1 kilohertz frequency. We'll hook in series resistance of 500 ohms and a capacitor of 0.159 microfarads. That means the impedance of the resistor, it's 500 ohms, right? It doesn't vary, it doesn't depend on frequency, nothing's different. The impedance of the capacitor is 1 over j omega c, right? It depends on the frequency, and so that's 1 kilohertz. So we find the angular frequency is 2 pi times the frequency, and then times the capacitance, and then 1 over. So we have, if you do all that math, you end up getting that the impedance of the capacitor is minus j 1000 ohms. And so essentially the impedance of the capacitor in this example is twice that of the resistor. So if we write down the voltage of the signal generator, we can do that. We can write it in the polar form. This is just an oscillating function. Remember from our last slide, this is just the voltage divider. We know how to write down the voltage across the resistor and the voltage across the capacitor. So the voltage across the resistor is the impedance of the resistor over the total impedance of the circuit times the voltage of the signal generator. And if you go through, substitute everything in, the resistance, the capacitance, the frequency, the values we calculated before, you get the following value. You can do the same thing with the capacitor. And so you have something all oscillating. And maybe the first thing to notice is they all oscillate with the same frequency, right? Omega is exactly the same for all of them, but they don't have the same phase, right? So they don't all start at the same spot, and so they're not in phase anymore. Now let's look at a graph. So we have the voltage of our signal generator. We wrote that down from before. We figured out the voltage across the resistor and the capacitor. And so this is, if you plot that, that's what this looked like, right? Here's our cosine. We started at maximum. That's our signal generator. And then we have the voltage of the capacitor, which has a different phase, and the voltage of the resistor, which has a different phase. And so the main point is that at every instant of time, the voltage of the resistor plus the voltage of the capacitor should equal the voltage across the signal generator. And if you go through point by point, that should indeed be the true, right? When the voltage across the resistor is equal to the signal generator, the voltage across the capacitor is 0. When the voltage across the resistor is 0, the voltage across the capacitor is that of the signal generator. So that appears to be true, but this graph sort of illustrates how complicated it now is, right? Things aren't always in phase as we did when everything's just a resistor, but the mechanism to get there is exactly the same, and we just kind of have to plot it and kind of make sure does our answer make sense.